So let's do this. I'll just put up here what we've done so far. We started off with the power rule. We learned that. And then we said, hey, there's also the product rule. We also said there's the quotient rule. And so the product rule applies if it's the derivative of a product. The quotient rule applies if it's the derivative of like a fraction. We looked at some of the cases where maybe the quotient rule wouldn't be best, but that's where it applies as well. And there's only one more situation, and that is, that we're going to look at here in the first semester, what if it's not a fraction? What if it's not a product? What if it's a composition? What if it's a composition of functions or a composite function? So I would like to ask you, first of all, do you guys remember from like pre-calc algebra 2 maybe, what is a composite function? F of g of x?
Yeah.
Sure, yeah. So you can see it kind of coming up down there. But yeah, so a composite function would maybe be noted f of g of x. I agree. But like, does that mean f times g of x? Is this like multiplication?
You put a function in as the variable of another function.
Yeah, or maybe the input? Yeah. So Eden said it pretty well. She said you put a function in as like the input of another function. Right? So if this I think you can do this. If this has to do with multiplying two functions together, and if this quotient rule has the idea of dividing two functions together, like that's what's going on, composite. It's not multiplication, it's not division, and it's not addition or subtraction either. So mathematically, what is composition? There is a single word answer for this. Say again? It's substitution. Yes. So it's taking the input out of one function and replacing that input with this whole other function. It's substitution, yeah. So if we have this substitution concept, then how do we deal with that? That's kind of the idea. So a composite function, I'll just write a few more things down here. It is a function as the input for another function. You could say, like I think we said originally, it's a function within another function. That's very true. And so if we are differentiating a composite function, we've got to use the chain rule. So this is the third, I guess you could say fourth rule if you want to count the power rule. The fourth main, really significant rule we've looked at. It's the last one in the first semester. Product rule, power rule, quotient rule, chain rule is the last one. And I think this is where even those that took DC pre-calc, I think this is maybe the last thing you looked at. Am I right? Kind of, sort of, like, I know by the last thing you looked at, it probably was like May 10th. And so you're like halfway mentally checked out as it was. And so do you remember this? Maybe, maybe not. That's okay. It's okay. So there are a couple of different ways to look at the chain rule. The real classic way is right here. And I don't often present it that way. It's a good way to look at it. You're going to see me present it typically this way, and I do have a demonstration to help you with this. Sadly, there is no cutesy little saying like 1d2 plus 2d1 or low d high minus high d low over the square of what's below. Nothing that rhymes. I mean, I can tell you a phrase, but it doesn't really rhyme, so it may or may not stick. So instead of a phrase, I've got a little demonstration for you. So I'm just going to kind of leave that up there, and I think maybe I'll just leave the video running. This will not come through very well in the video, but hopefully you'll hear the description. So I've got a box. Has anybody ever done this or had this done to you where it's your birthday or it's Christmas or something where you exchange gifts, give gifts to somebody, and you have either made this or received this, where you get this box, it's a present, right? So you unwrap it, even when you get older, you're still like, ooh, what's in there, right? You're like, somebody gave me something. That's always exciting, right? So you unwrap it and there's a box, right? So what do? You open the box, right? Okay, it's over here. I open the box. And what's inside? Another box. You ever done this to somebody? Have you had it done to you? Yes. I mean, it's like sort of funny, depending on the scenario. But yeah, it's like a box within a box. You're like, oh, cool, you gave me a box. So what do? You open this box, right? And you open this box, and maybe inside this box there's the actual present. Possibly. Somebody gave this to me a while back. This is a pooping Santa. It's got brown jelly beans in there. It's extremely old, and he broke. So what you're supposed to do is pull his arm, and his back end is supposed to open, and there's like little Yeah, it's kind of like a pull my finger scenario, yes. Yeah, there's little brown jelly beans in there, and they sometimes...
I think it was like...
Anyways, whatever. I'm sure you anyways, so this is the scenario where you look at it and you're like, well, when you look at it from the outside, you really don't know what's going on in there, right? But you open it, and you open it up, and there's a box. And you're like, whoa, okay, so I got this box in here. What do I want to do? You finally open it up, and maybe that's your present. But couldn't this go on forever? Couldn't somebody give you a box, and then there's another box in there, and then inside that there's another box, and then couldn't there be like 10 of these boxes? And that would be the more fun way to do it, have like 10 boxes nested together, and you open them up and eventually get to hopefully what would then be a really awesome present, right? If you go through all that work, right, opening 10 boxes.
When I do it, I put a rock in there.
You put a what in there?
Like a rock.
A rock.
Yeah, when I did my sister, I gave her a penny.
It either has to be really terrible like that or really awesome, right? One of the two. Gentlemen, I don't know if I recommend this as like a, later on if you want to marry somebody, like a proposal technique.
That would be so fun.
I said I don't know if I recommend this. I mean, you got to know the girl pretty well. You know, if you think she'd be down for that, cool. If you think it would just like make her mad, probably not the scenario you want to like propose to her. I don't know. You just got to know her. Anyways, so this is actually an illustration of the chain rule. So, as you guys mentioned, a composite function is basically a substitution. It's one box inside another box, or one function is the input for another function. That makes sense? And so what I want to do is I want to kind of, you can see the rule here, and I can tell you the little phrase that you could maybe think about here. So the phrase is awkward, and that's why we don't really have a phrase for this. So the derivative of a composite, so the derivative of f of g of x is equal to the derivative of the outside with the inside still in there. See why this is awkward? That's why I don't have this phrase. So it's the derivative of the outside with the inside still in there times the derivative of the inside. So sometimes people will shorten this a little bit, and it's a little misleading to say it this way. Sometimes people will say the derivative of the outside times the derivative of the inside. But that misleads people sometimes because they don't realize that it's the derivative of the outside with the inside still in there times the derivative of the inside, and then what if it's like 3 or 4 boxes all nested together and that one kind of falls apart? I'd rather show you a demo. Go ahead. Don't try to memorize that. I mean, I don't know.
No, I was going to say, like, so does that mean by the derivative still on the inside, do you just mean, like, once you plugged in g of x to f of x, like, the derivative of that times the derivative
No, so notice that, like, in that first piece of the chain rule, it's f prime of g of x. It's not f prime of g prime.
Gotcha.
So, right, so the inside is still in there, like the original inside is still hanging out in there. And here's the analogy with the boxes. So, guys, listen. This works. This should help you remember this. So if you've got a box within a box within a box or something like that, like what a composite function is, here's the scenario. When I open the first box, opening the box signifies I'm doing a derivative. Fair enough? So I'm opening the first box, and there's another box in there. Now, is that box open right now? It's not. That's why it is f prime of an unopened box. Right? So it's f prime of g of x. Well, then what I do is, I'm like, look, it's a box. So I take it out, and what do I do with it?
Open it.
I differentiate it, right? I open it. I set it to the side, and I open it. That is this right here, g prime of x. Okay? So you open the big box, and look, there's another closed box in there right now. That's f prime of g of x. And then you take out that box, and you set it over here, and you open it. That's differentiating, signifying you're differentiating the inside. Now, this could go on forever, right? Maybe not forever. This could go on for a really long time. So let me erase all this awkward wording here. And let me just show you an example of how this could go. This is going to be a really extreme example, and I don't think that I would ever ask you to do this. Just from a time perspective, this would take forever. But let's say that I had you do something like this. d dx of f of g of h of L of x. 1, 2, 3, 1, 2, 3. So this is not a function inside another function. This is a function inside another function. That whole thing's inside another function. And then that whole thing's inside another function, right? So this is still just the chain rule. So check this out. Let's see if we can see how this would work. What you do is you unpackage the biggest box first. You open it up. What's the biggest box? F, right? It's the outside box, the biggest one that all the other ones are inside of, right? So the first link in my chain would be F prime with all the other boxes still in there. One, two, three, four. There we go. Then what I would do is I would open up the next biggest box, the first one that I come to. What is that next box I'd come to? G. So this would be times G prime of H of L of X. Then what is the next largest box? H. So times H prime of L of X. And what's the tiny box? L of X. So then finally it would be times L prime of X. So please notice that each time all I'm doing is I'm like opening up, aka differentiating, the next box that I come to. I can't see the other boxes yet, right? So I open up the big box, and all those little boxes, they're still in there. Then I open up the next one that I see with all the other little boxes still inside that one. Then I open up the second to smallest box. And then finally I open up the tiniest box. So it's called the chain rule because it's like links in a chain. And that chain could just get longer and longer and longer depending on how many functions are packed in there into the box, right? So, you'd say this is like link number 1, link number 2, 3, and 4. So there were 4 functions. So if there are 4 functions, there better be 4 links in your chain or 4 boxes that you're opening. Make sense? So since there's not a cute little 1d2 plus 2d1, low d high minus high d low square what's below, I've got the boxes. So if you can picture the opening of the boxes being a derivative, hopefully that's enough to help you remember. Is that okay? Okay, awesome. So then the truth is, this will maybe be hard to wrap your mind around at first. The truth is, when you first learned how to do the power rule, when you first learned how to do the product rule and the quotient rule, believe it or not, you are doing the chain rule. You just didn't know it. Okay, and I'm going to kind of explain that to you right here as we talk about this general power rule down below. So if you would, look at that, and I'll get there here too. Okay, so the general power rule is this. So this is d dx of u to the n, and u stands for some function in terms of x. So who knows what it is? It could be super duper simple, just like x, or it could be like sine of x times cosine of x, or a quotient, cosine of x over x to the 4th. I don't know, but u is just some function in terms of x. Here is the general power rule. We would say that d dx of u to the n equals n times u to the n minus 1, which you're familiar with, right? This is the standard power rule. But we would also have to multiply this, according to the chain rule, by the derivative of the inside. And u would be that inside function, something to the n. So I'm going to illustrate this for you guys, how we have always been doing the chain rule, even if you didn't know it. Well, check this out. I'm going to say y equals something to the 5th power. And we'll just kind of fiddle around with this a little bit. So what if I said y equals x to the 5th power, and I want to know what dy dx is? In other words, let's find the derivative. So if I do d dx of all this, I would get dy dx equals d dx of x to the 5th. You might look at that and be like, well, duh, the derivative of x to the 5th is 5x to the 4th. Totally right. Totally right. But here's what I'm going to do. I'm going to look at this x to the 5th. I'm going to try to I know it's not really a composite. It's very trivial. But yes, sir.
Are dy dx the same thing is that the same thing as dx?
Okay. So let me rewind a little bit. No. So d dx is an action. d dx is saying, hey, Santi, do the derivative with respect to x of whatever comes next. dy dx is a noun, so like dy dx would be like, find the slope of the tangent line. So let's see here. I'll come back to that. So d dx is an action. So if I said do d dx of x to the fourth plus 3, that's basically saying do the derivative with respect to x of x to the fourth plus 3. So like telling you to do something.
Okay.
If I said do dy dx, you'd be like, well, what's y? Right? You'd have to, if I wanted you to find dy dx, wouldn't you say, well, okay, I could do that if you would tell me what y was. Over here, I'm essentially telling you what y is, and I'm saying do the derivative. So d dx is an action. So if you see d dx of something, that's saying, hey, do the derivative. If you see dy dx, that means I either need to tell you what y is, or I'm just giving you some information about dy dx. I might say dy dx equals -3. That just means the slope of the tangent line of y is -3.
Got it.
That make sense?
Yeah.
Okay. So let me go back to this. So I told you that the general power rule was this. Okay? And then I said, let's come over here, and I want to look at this right here. I would like to look at this as a composite. Okay? I know that you probably are thinking that it's not a composite, but if I changed it, if I said, you know what, instead of an x, let's make it a cosine. Are you guys okay with that being a composite? Okay? But I want it to be an x for right now. So it's back to being an x. So here's what we've been doing this whole time. We've been saying, hey, you know what? This is equal to the power rule. The 5 comes down in front, and we subtract 1 off the old exponent. And now here's the chain rule factor. What is d dx, the derivative with respect to x, what is d dx of x? 1 times 1. Well, what's 5x to the fourth times 1? 5x to the fourth. And so it would have been really silly if I would have said, hey, let's learn this power rule. And oh, by the way, the derivative of x squared is 2x times 1. And the derivative of x cubed is 3x squared times 1. You would have been like, what's with all the times 1s? It's silly, right? But maybe now it's not so silly. Check this out. What if I said y equals, maybe like I said before, cosine of x, quantity to the fifth? Now the chain rule factor isn't going to be a 1. Right? So if I do the derivative, I'm going to say dy dx equals 5 times something to the fourth cosine. But now when I multiply by the derivative of the inside, the derivative of the inside, it ain't 1 anymore, is it? It's negative sine x. So I would call the things that I'm highlighting in orange, I would call those the chain rule factor, right? It's simply the multiplying by the derivative of the inside. And when the inside is an x, well, then the chain rule factor is just a 1, right? So it's no big deal. Like, we don't really need to write it. But if the derivative of the inside is something other than 1, you have to write it, don't you? Because it's not 1. And so we've always been doing the chain rule. We just never wrote the times 1 because there was really no need to write the times 1. Now, if the insides are different, then you're going to have to write the times the derivative of whatever that inside is. Okay? So let's run through these. This will be excellent review when we think about your quiz tomorrow. If you look at all these derivatives lined up below and you think, oh, gee, I don't remember what the derivative of that is, this will be another chance for you to hear it, to see it, to do it. Definitely for your quiz tomorrow, got to know this stuff. Okay, so here we go. The derivative with respect to x of sine u. What's the derivative of just sine? Cosine. So we would say the derivative of, with respect to x of sine u would be cosine of u, but now we got to multiply by the chain rule factor. So you could multiply by times u prime. So we don't know what u is. U is just some function in terms of x. U could just be x, and if u is x, the chain rule factor would be 1. But if u is something other than x, like cosine or e to the x or whatever, then that chain rule factor of u prime is going to be something totally different than 1. So it's got to be there. The derivative of cosine u would be negative sine of u times u prime. Exactly. Or you could say, if you wanted to, you could say times du dx. Same thing. Different notation, same meaning. Do you guys remember the derivative of tangent? Not cotangent. I want to get this answer first. Derivative of tangent has to do with secant squared. Yeah, secant squared. So this would be secant squared of u times u prime. Ed.
So if it was like cos and then like a different variable, just say it's an h or something.
Yeah.
It would be dh over dx.
Yes. That's awesome. That is an awesome insight. We will use that for sure. That is really good insight. Okay. And then what about cotangent's derivative? I heard a cosecant. It's negative though, right? So it's negative cosecant squared of u times u prime. All right. And then the last two, the derivative of secant is? Secant tangent. Yeah, so this would be secant of u times tangent of u times du dx, or u prime. I'm just kind of mixing up those symbols because they all mean the same thing on the right there. So I want you to be comfortable using both. And then lastly, the derivative of cosecant would be? Except it's negative, right? Hi. So negative cosecant of u times cotangent of u. Man, you missed the box. You missed the box demonstration. Man, if you don't show up at the start of class, you totally miss it.
I know.
You should just be on time next time.
I'll try my best.
All right. So anyways, like I said, this is obviously moving forward with the chain rule. Also good review for your quiz tomorrow. You guys good? Say it one more time. If you don't know this stuff, it's gonna be painful.
Okay, I'm confused with the dy dx.
Say again?
I'm confused with the dy dx cos of u, and then also c.
Okay, hold on. Oh, it's du dx. So basically what I've got here is like all of these things that I'm circling in orange. Those are all the chain rule factor, right? The times the derivative of the inside or times the derivative of the little box.
Yeah.
And what I'm doing is I'm mixing up my symbols here just to help you remember that u prime is the same thing as du dx. So like they're interchangeable. So if you wanted to write u prime there, I'm good. If Anna wanted to write du dx, she's good too. Yeah. Okay. So we're just going to do a few examples here. So our class is done at 25. So I think we'll take probably about 6 or 7 minutes to do a couple of examples here, and then we'll pick this up again on Friday after we do your quiz tomorrow. Does that make sense? So let's do number 1. So if you guys could check that out. And I do want to kind of help you through this a little bit. This first one kind of demonstrate how the box thing and how the stuff we just did kind of plays into this. But before we do that, we need to make sure we're good with the symbols here. Can anybody rewrite sine squared of x using different symbols, but it would have the same meaning? Like, what does that really mean? Say again?
Did you say f of x is equal to sine of
So you could turn it into f of x if we wanted to call it f of x, or somebody could call it g of x. I'm okay with that. I'm more thinking about the right side. Like, what could I do to the right side?
Could you move the 2
Move the 2...
to the right? Because it doesn't not matter when you
Well, so that's part of the issue, though, right? So if you wrote it like this, y equals this is part of the debate, right? So
doesn't it need parentheses?
So that's the issue, right? So like if you write it like that, you have to ask yourself, what's being squared? Is it the input or is it the output? Because if you put parentheses here, that means one thing. But if you put parentheses there, it means something else entirely, right? Mm-hmm. And so we just want to make sure that we understand what that actually means. And I think you guys have the right sense of it. It means y equals parentheses sine of x quantity squared. Yeah? It's really important that we keep that straight, like where the parentheses go and what it all means. So with that in mind, it's a little more clear that this is composite, right? You see it? Okay, so remember we said that a composite function is essentially substitution, where you're substituting one function in for the input of some other function. So let's see if we can identify these real quick. What would you guys say is the inside function for this particular one? Sine of x. Yeah, that's the input, right? So the inside function is sine of x. So that would be like the little box. What's the bigger box?
X squared.
Well, let's just say something squared, right? Like input squared. So yeah, I agree. So the inside box is sine of x, and the bigger box is something squared, right? Input squared. So here's how this would work. With the chain rule, I'll do the boxes here. So if we represented this situation with boxes, what would this box be? This would be the squared box, right? Something squared. And when I open it up to see what's on the inside, this would be the sign box. Okay, so here's how this works. I'm going to differentiate, and I can't differentiate the inside until I've differentiated the outside, right? Because I mean, right now, I don't even know if anything's in there. Could just be an empty box. I just don't know. So as I differentiate this, as I open this, I'm really differentiating the squared, right? How do you differentiate something squared? Isn't that just a power rule? So I open this, so this is going to be y prime equals 2 times whatever's in there to the first, right? And I open it up, and what's in there? Sine of x. Oh, okay. So there's a sine of x in there. Well, now I would really like to know what's inside the sine of x box. So I take it out, and as I open it, that's really differentiating it. And what's the derivative of sine? Cosine. So times cosine of x. And that was the only other box. There were just 2 boxes together. It's not like there was 3 or 4 like that other example we looked at. That makes sense? Yes, ma'am.
How do you know that that's a composite function?
Just by the way that it's written. So it's basically based on its characteristics. So if you saw, if I wrote some other function, if I wrote like f of x equals sine of x times cosine of x, and I said, Bailey, how do you know that that's multiplication? What would you say? There's a little dot right there. Yeah. Just the same way if I said g of x is equal to x over tangent of x, how do you know that that's going to be a quotient rule? See the fraction, right? You see the division there. So how do you know this is composite? Because it is a function inside another function.
But it doesn't like tell you. So is sine of x a function?
Yeah. Yep. So sine. So you know like there's 2. You could break this apart. So like in pre-calc, I think you probably did this. Maybe algebra 2. If you didn't, then I'm going to encourage strongly that they do this. You can take a composite and you can break it apart. So like if I told you that f of g of x was sine of x quantity squared, and then I said, well, what's f and what's g? This is kind of what we did. We did this kind of verbally earlier.
Would f be x squared and g be sine?
Mm-hmm. So you could recompose these by saying, well, f of g of x, that means...
Because the whole thing is squared, so that lets us know that like there is another function inside of there.
Yeah.
If only one part was squared, it's not composite.
What do you mean one part is squared?
Like if it was like sine x squared. Not
Well,
quantity
okay, then that would be a different composition. That is still composite, though. So, like, here's what you would do. So check this out. No, this is good. Let me explain this. So if I said, here's another way to look at this. If I said, I'll use f's and g's a lot here, so please forgive. But so let's say we did it the other way. Let's say I said f of x equals x squared, g of x is equal to sine of x. And I said find f of g of x. This is like probably very algebra 2-y, pre-calculus kind of thing to do. So what you could do is you could say, oh, okay, so I'm putting g into f, right? So f is the squared function. So you could write this, you could say f of g of x equals blank squared, right? Because that's the f function is input squared. Well, my input isn't just an x, it's g of x. Does that make sense? And g of x is sine. Now check this out, though. So I'm going to use these same 2 rules up here. I'm going to use those. Is this benefiting everybody? Is this making sense? I think it's good to like break these things apart because I think her question of, well, gee, what is a composite function and how can I tell? Like that's a pretty important thing because if you can't tell that it's composite, you won't be using the chain rule very much, right? Yeah. So you could do this in other directions. So I'll do this in a different color just so you can see this is different. So I asked you to do find f of g of x first, but couldn't I ask you to do it the other way? I could say find g of f of x. That's different, right?
Well, then you would plug in the x squared.
Exactly. So g is the sine function. So this is basically saying sine of something. And so the input is f of x. So it's basically saying find sine of f of x. We know that f of x is x squared. So it's that.
So then would that just be...
So you want to do, let's do the derivative of that. So this is a totally different question, but it's very related. So let's say that...
Still composite.
Still composite, absolutely.
And then
you could, like I said earlier, you could really look at every function as being composite. It's just that some of them are trivial because the input is just x instead of cosine of x or x squared or something.
Is number 2?
Totally composite. Yeah, we'll try to get there in just a second. Let me show you the other way. Maybe this will help clear it up for you. What if I said y equals sine of input squared? This is different, right? Because the first one I gave you right here, it was the input was sine of x, and we were essentially squaring the output, right? So on this one in purple, I'm squaring the input. So here, we'd say, okay, what's the big box? Sine is now the big box. And what's the derivative of sine? Cosine. So when I start to write the first thing in my chain, I'm going to write y equals cosine of blank. Well, I open it up, and what's in there? What kind of box is this? It's the x squared box. Okay, so there's another box in there. It's not just simple. So then I look at this and I'm like, well, I would like to open this. And as I open it, I'm differentiating the x squared box, which is 2x. So times 2x. Does that help? Seeing it forwards, backwards? Did I answer your question?
Yeah.
It was a very deep question. It wasn't just like a 2-second answer.
Yeah.
Okay. I hope I didn't confuse anybody. Are you okay? What's that?
That definitely helped.
Okay, good. Yeah. We gotta break this down. And like I said, this is a prime example, and thank you for your question. Like, I'm starting to get to know you. I still can't read Andy's face very well. But sometimes I look at your face and I'm like, I really don't know what you're thinking. Like, I'm getting this, I'm not getting this, right? This little tiny question is actually a big question, or what I think is a big question is actually a little question. You got to ask it. So thank you for asking. Let's do one more. This will cut into our Q&A time a little bit, but since you asked, let's go ahead. Is that okay? Do number 2? Okay, so let's fast forward to number 2, and we'll look at why that's composite and what it actually looks like for a derivative. Okay, so for f of x, like we've kind of gotten into practice of this already, but whenever you see a radical, like this is fourth root, we should always rewrite radicals, I think, with a fractional exponent. So what is the fourth root really? 1/4. To the 1/4, yep. So it would be f of x equals -3, parentheses, all this stuff, all to the 1/4 power. So I feel like when you write it this way, it's maybe a little bit more clear, the whole compositeness of it and the inside function and the outside function, the little box and the big box and all that. Yes, ma'am?
If there were, actually, never mind. That's the question. Never mind.
Okay. So let's approach this from the idea that maybe on some test in the future, this is like number 7, and all it says is find f prime, right? So here's what you would do. You would look at that, and you'd say, is this going to take a product rule? You could technically sort of do a product rule. You could say that like the 1 is -3 and the 2 is all the other junk. But since the 1 would be a constant multiple, I say let's not do that. Let's just think of that as a constant multiple. So could be a product, but let's not do that. Clearly, the way that it's written here, it's not a quotient either. So is it something else? Can you see that it's a function within another function? Can you recognize that? That it's not just x to the 1/4. It's like this whole big mess to the 1/4, right? Whole other function.
Why is the notation not written as like f of something of x?
Well, so you can, like, the f of x, the g of x, the h of x, whatever it is, that's just the name of a function. Like, if a function is composite, it doesn't have to be named f of g of x. Like, what's your middle name? Okay, sorry. Anybody want to share their middle name? Anybody want to share their middle name? Come on. T? Just like the letter T.
It's T-H-I, but you said T.
T. Okay, so if I said Eden T. Macarag all the time, wouldn't you guys think that was weird?
Yeah.
What if I even just use your first and your last name, Heather Brandon, do you have a question today?
Okay, some people you have to do that.
I get that, but if I did that with everybody, wouldn't you be like,
Bailey Sue, you could start calling her Bailey Sue.
Bailey Sue Waters, how's it going today? Wouldn't that get awkward, especially if I did that with every single person?
Yeah.
So
It's
you
just
don't,
unnecessary.
yeah, it's just unnecessary. You just say, hey, f of x is this, and it could have like 27 different functions nested within each other, and you can still just call it g of x. It's okay. It's okay. So they won't always call it out like that, though, Anna. Sometimes they will call it out. Sometimes I'll say, hey, f of g of x equals this, blah, 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 find something. Yeah, Audrey. Audrey Perlman, yes.
Would a parentheses cue you to use the chain rule?
Yeah, parentheses are very common. Yeah, I would say that's, we could easily write counterexamples to that,
Okay.
but I think parentheses are a big hint. Yep. Okay, let's do this really quick. What is the outside function? What's the big box? It's -3 something to the 1/4, right? -3 input to the 1/4. You could just think of the bigger box as just -3 times we don't know, and frankly, we don't care yet, all to the 1/4. That makes sense? Just -3 times something or other to the 1/4. We don't really care what's in there yet. So how would you guys differentiate -3 times something to the 1/4? That's power rule. Yeah, you're doing it. Yeah. So it'd be f prime, you said it right, equals -3/4 times all that junk, and then 1/4 minus 1, -3/4. It is just a coincidence that those two numbers match. Don't think that they always do. Now, once we've opened that bigger box, we've seen, hey, you know what? There's kind of a complicated box inside that box. So it's, x squared minus 2x plus 1. So now we have to multiply, because of the chain rule, times the derivative of that smaller box. And so what is the derivative of that smaller box? 2x minus 2. And there's no more derivatives to be had. There's no more composites to be unpackaged, if you will. Chain rule, you always multiply your links of the chain together.
Will we get to a point where we can, we'll recognize multiple inside of each other?
Sure. We're going to do some on Friday. I'm not going to go probably past 3 functions nested. Just from a time perspective, it just takes forever.
Yeah.
Yeah. Okay, guys, I think we'll stop it right there for now. We've got like 7 or 8 minutes left. Do you have any questions on